Hello and welcome to another power system analysis class. In the previous class, we concluded transformers. Uh, we solved problems on ideal transformers and non-ideal transformers, and how we can determine a non-ideal transformer parameter using the open circuit test and short circuit test. Today, we're going to start with per unit. We are specifically interested in three-phase per unit. I would solve problems for one-phase and three-phase per units, and then we will solve problems on three-phase transformers, loads, and generators. I will also post homeworks on transformers, non-ideal transformers, so you can solve and after that I will post a solution for them so you can practice and solve more of those type of questions, the questions that I solved in the previous class. So previous class we reached the part which was grounding. This shows a graph of a service entrance grounding system. We'll talk more about grounding in future lectures. I just wanted to show you a schematic of how the entrance grounding system works. And in the transformer, as mentioned, we ground the system, and the reason it makes the system much simpler and easier to handle. And also, if we have a three-phase star system, we balance that system and try to ground the neutral point. So again, I would talk more about the grounding that we started the last week. Now, for per unit calculation, a problem that we have in power analysis is when we have multiple transformers. So for example, imagine we have a transformer at the load, which is a step down, and then we have another transformer at our substation, and then we have another transformer at the state level, and another transformer at the generation. So for example, the one at the generation side, this steps up the voltage from, let's say, 120 to 10,000 volts, then to 50,000 volts, and then down back to 5K and so on. And eventually you're going to have one that it goes down to 120. This is just an example. It's not the exact numbers. Now, when you have multiple transformers, and imagine at the end you have a load of 10 ohms, it becomes very difficult to transfer that load to the generation side because you have multiple stages. And as you know, when you want to transfer the load to the secondary to the primary side, the new load, or Z, let's say Z2 prime, would be A square Z2. And as you know, A is our turn ratio. Now imagine if we have 10 stages. You have to multiply by A1 in the power of 2, then A2 in the power of 2, and then A3 in the power of 2, and it's going to just cascade. And it's becoming very difficult to keep track on that. In addition to that, keep in mind that each transformer is a non-ideal transformer. So with that, you're transferring the load, the transformer resistance, and the line resistance all together. So you're just adding together, and it becomes very complicated at some point. So to make it simpler, we use a method called a per unit system. A per unit system normalizes all the variables, and this normalization is also known as per unit system. And a quantity in per unit is equal to the actual quantity divided by the base value of that quantity. And that could be voltage, could be power, could be resistance, and so on. I will give you more example. Let's start with the easiest one, with the one phase per unit conversion. So for one phase, we will pick one phase volt amp base, or the apparent power base for the entire system. And we call it SB, or the base apparent power. Then we will pick a voltage base for each different voltage levels. So if we have 3 levels, we would have 3 different voltage base levels. If we have 3 different transformers. And VB voltage bases are related by transformer turns ratio. And the voltage, this is very important, are line to neutral voltage. So we are calculating only VLN. We are not using V line to line. If there is V line to line, you have to convert it first to V line to neutral. We calculate the impedance base using this equation. ZB would be equal to VB square, or the base voltage square of that level, divided by SB, or the apparent power of that base level. Then we calculate the current base, and IB using Ohm's law is going to be the voltage of that base over its impedance. And finally, if it's needed, we will convert actual values to per unit, and we can convert them back to the actual values as well, depending if we need them. Now, per unit, because we are dividing volt by volt, for example, they don't have any units, and they only so they example we don't have like 2 volts or 4 volts. It's just 2, because it's a ratio between that voltage and the base voltage. So for example, if V base here is 20 divided by 200, that would be, for example, 0.1 of V, our base voltage. It doesn't have any units because the units are already canceled out. So it's called 0.1 per unit of the base. 0.1 of base, or sometimes we call it 0.1 per unit of base. Now, since we are dividing the magnitudes, we also don't, this per unit doesn't have an effect on the angles as well. So it's only affecting the magnitudes. It's not affecting the angles. Now, to solve a per unit example, first we'll convert to per unit. Many problems that are given are already in per unit, but if it's not given, we will convert them to per unit. We will solve them, and then we will convert everything back to the actual values if it's necessary. Now, the best way to understand this is through an example. This is a per unit example for a one-phase system. Now, here you can see we have 2 transformers. The first transformer ratio is 5:1. The second one is 1:10. So we have the load, and here we have the generator. Now, in this case, the load voltage and load power are using per unit analysis with a base power of 100 megavolt amp. So S base here is 100 megavolt amp. And the voltage base is 8 kilovolts and 80 kilovolts and 16 kilovolts. So for the first one, it's 8 kilovolts, and then we have 80, and then we have 60. Now, let's solve the example. Now, first thing that we want to do, we want to find the base impedance. And for the base impedance, we use this equation. And by the way, all the equations that we need are here. We don't need anything else. Now, the base impedance is going to be V base square over SB. And what is V base square in this one? For the first stage, it's 8 kilovolts square over 100 megavolt amp, gives us 0.64. And this is per unit, basically. The middle one is 80 kilovolts square over 100 megavolt amp. It's going to be 64. And the last one is going to be 16 right. Again, it's put this left, middle, right, so you won't be confused. And the last one on the right is going to be its base voltage, which is 16 kilovolt square over 100 megavolt amp, gives us 2.65 ohms. Now we can simplify this and simplify model to this one down here. Now we have replaced the generator, which is 8 kilovolts, to 1 with a degree of 0 degrees. Again, it doesn't have any effect on the angles. And then what we do is we will convert every single one of these impedances. Now, to find I would be equal to the voltage base over the impedance. Now, the impedance here is going to be 3.91, which is the resistance, plus the inductances, so the real part plus the imaginary part, which gives us 3.91 plus, if you add 0.39, 0.375, and 1.56, we reach J2.327. In other words, the current would be 0.22 with a degree of negative 30 with the 30.8 degrees. And this is in per unit, it's not in amps. And if we want to find the voltage of the load, we can simply multiply that current by the impedance. This is one way to do it. Or another thing that we can do, we can simply do a simple KVL, which has been done here. You can do a simple KVL, and you can start from here and get to this VL. And if I want to do this, it's going to be 0.0 with a degree of 0 degrees minus 0.22 with a degree of negative 30.8, which is our current, times this impedance, which is J.56 plus J.375 plus J.39, which gives us 2.327, which is technically this one, with a degree of 90 degrees because it's 9J. And then we reach VL at 0.859 with a degree of negative 30.8 degree. Again, there's another way to solve it using Ohm's law as well. Now, the load power, SL, would be VL IL star, or conjugate, which is going to be equal to VL square over Z, same thing that we had, gives us 0.189 per unit. And the generator power is going to be 1 times 0.22 with a degree of 30.8, gives us 0.22 with a degree of 30.8. Again, SG is VIG conjugate. So if I is 0.22 with a degree of negative 30.8 degrees, I conjugate would be the same magnitude, 0.22 with a degree of positive 30.8 degrees. Now, to convert back the actual values, we just multiply the per unit values by their per unit base. So the actual value of VL, which is the voltage on the left side, it's going to be, just give me a second. On the right side, I'm sorry, V load. This is V load. It's the one on the right side. It will be 0.859 with a degree of negative 30.8 degree, the one that we found here, which is our VL, or this voltage. And we will multiply it by 16 kilovolts that we had for the right side. This one was 16 kilovolts, 80 kilovolts, and this was kilovolts. So multiplying that gives us 13.7 with a degree of negative 30.8 degrees kilovolts. And the actual apparent power would be 0.8189 with a degree of 0 degrees times 100 megavolt amps gives us 18.9 at 0 degrees. And the actual generation apparent power would be 0.22 with a degree of 30.8 degree times 100 megavolt amp gives us 22 with a degree of 30 degree. The middle current would be 1,250 amps, and the actual middle current would be 275 with a degree of negative 30.8. Now, that was for one phase. For three phase, it's very similar. It's almost exactly the same. But the only difference is in a single phase, we use line to neutral voltage. In three phase, we use line to line. So this is the only difference. This is important. We use line to line voltage for a three phase. So procedure is similar to one phase, except we use a three phase VA base and use line to line voltage bases. Now the procedure is as follows. We pick a three phase VA base for the entire system, or the apparent power of the three phase. We pick a voltage base for each different voltage levels, VB. Voltages are line to line, again, very important. And so three phase power combined and voltage of line to line. And then we calculate the impedance base, which here impedance would be V base line to line square. And we know that V line to line is equal to square root of 3 V line to neutral. For a star. And by the way, we're doing all of this in star. So we replace V base line to neutral, which gives us the square root of 3. And square root of 2, 3 in the power of 2 gives us 3. 3 cancels 3. We are left with V square of B ln over S one phase of B. Now, this equation for ZB, does it look similar to this equation? Yes. So it becomes the exact same question for the impedance. So when we are solving for three phase, we are technically solving for three separate one phase systems, and we can combine them. So exactly the same impedance base as with single phase that we had. And we assume that the phases are balanced. We share the same, impedance and all of that, and inductance makes our job much easier. Therefore, if we solve for one phase, we have the answer for all three. Now, three phase per unit. The next step that we do procedure is to calculate the current base. Now, the current base would be equal to, of the three phase, is going to be the apparent power divided by square root of 3 VBLL of line to line. We can convert it to line to neutral, and we get S of one phase. Again, 3 cancels this 3 over VBLN, which again is the exact same thing as single phase. So if we go back to single phase, you can see that IB is again V base over ZB, and when we calculate it, it's going to be SB over VBLN. And finally, we will convert actual values to per unit. And when we can solve it and convert the per unit back to actual values by multiplying it by the base. Now, for the following example, it's a three-phase per unit example. We want to solve for the current, load voltage, and load power. In the previous circuit, assuming a three-phase power base of 300 megavolt amp, and line-to-line voltage base of 13.8 kilovolts, 138 kilovolts, and 27.6 kilovolts. the square root of 3 larger than the one-phase example voltages, a little bit larger. Also assume the generator is Y connected, so its line to line voltage is 13.8 kilovolts. Now, first we have to convert to per unit. As before we start, again, this is the original circuit that we had. The only thing that we changed was the voltages, and now it's 13.5 and so on. So these voltages and the total power is multiplied by 3, so it's 300 megavolt amps for the 3-phase. Now, again, converting it would be exactly the same, and we reach the same impedances that we had. Okay. Now, first we want to find the current I, which will be our base voltage, which is 1 with a degree of 0 degrees, divided by the impedance. Again, the impedance is 3.91, the real part plus the imaginary part. And if we add these, 1.56 plus 0.375 plus 0.39, we get 232.7. I'm sorry, 2.327. All of them are J. So this would be our impedance, and the per unit amp would be 0.22 with a degree of negative 30.8 degree. Again, the unit doesn't have any unit, it's just per unit because it canceled them out. VL is going to be 1. Again, we do a KVL from here to here. It's going to be 1 minus this impedance. I'm going to call it ZJ times the I gives us VL, which is going to be 1 minus 0.22 with a degree of negative 30.8 degrees, which is our I, times the impedance, this impedance that we have here. And gives us a VL of 0.859 with a degree of negative 30.8 degrees. Now, if we want to find the load power, which is going to be VL-IL conjugate, or in other words, VL squared over Z. We already have VL, put a power of 2, and we have Z. The answer would be 0.189 per unit. And if we want to find the generator apparent power, we use the VI conjugate again. And we already have I. I conjugate would be this with a degree of positive. And the answer would be 0.22 with a degree of 30.8 degrees. And you can see that's exactly the same as a single phase. So what we can do is, instead of solving it for 3-phase, we solve it for 1-phase, assuming everything is balanced and the same impedances apply. Now, the differences between 1-phase and 3-phase appears when we convert them back to the actual value. So in per unit, they're going to be the same, but when we convert them back, you can see that the total power is going to be different. Now, VL actual is going to be 0.859 with a degree of negative 30.8 degree, which was the per unit, times the base, which gives us 23.8 with a degree of negative 30.8 degrees. S actual is going to be the same, the per unit times the base gives us 56.7 with a degree of 0 degree megavolt amps. And the actual generation part is going to be, again, per unit times the base gives us 66 with a degree of 30.8 degree. The middle base current is going to be 300 megavolt amps divided by square root of 3 times 138 kilovolts, which was the middle voltage, gives us 1,250 amps, which is the same current. And the actual middle is going to be equal to 0.2 with the degree of negative 30.8 times 1,250 gives us 275 with a degree of negative 30.8 degree. Now, this is another example that I want you to solve at home, and I'll give you a quiz after this example. Assuming a three-phase load of 100 plus J50 megavolt amp with VLL of 69 kilovolt is connected to a source through the below network, what is the supply current and the complex power? The answer here is I is 467 and S is 103 plus 0.3 plus J 76 megavolt amps. The answer already given. I want you to go at home and think on this and try to solve it. I already provided the answer, so for your convenience. Now let's start with a small quiz. Do you have paper or? Yes. Can you give your friend this? Okay. Now, the question is this. We want to convert per unit impedance to ohms. A generator reactance is X is J.25 per unit. S base is 50 megavolt amps. And V base is 11 kilovolts. We want to find the actual reactance in ohms. I'll give you like 5 to 10 minutes to solve this. By the way, just for a reminder, Z base is equal to V square of the base over S. Did you solve it? Yes, perfect. Now, again, using the equation z base is equal to v base square over s base, which would be 11 times 10 to the power of 3 because it's in kilovolts, and this is in the power of 2 over SB, which is 50 megavolt amps. So 50 times 10 to the power of 6. Now, this would give us 121 times 10 to the power of 6 divided by 50 times 10 to the power of 6, which gives us 2.42 ohms. Now we want to convert per unit to ohms to actual values. So S of the actual value would be X per unit times Z base, which would be 0.25 because the per unit was 0.25 times the per unit, which is 2.42, gives us J 0.605 ohms. Okay, thank you. Remind me to give you extra points on your next exam. Now, per unit change of megavolt amp base. So parameters for equipment are often given using power rating of equipment as the megavolt amp base, meaning it's like 0.5 of megavolt amp base or 0.6 or something like that. To analyze the system, all per unit data must be on a common power base. So if we have an original power base per unit, we have to convert it to actual and then to a new base power unit. Hence, the way that we do it, we have the original base power in power units times V square base over S original base divided by V square base divided by S of the new base, which gives us a Z of new base per unit. In other words, the original base impedance times S new base over S original base gives us the Z new base per unit. Now, may seem a little confusing. This is the final equation, but let's solve it using let's solve an example to get used to this. We have a 54 megavolt amp transformer, and it has a leakage reactance of 3.69. By the way, usually we in power systems, in transformers, we show leakage reactance in percentage. We say it's like 0.2% or 0.4% or so on, or 4% or 5%. So here the reactance is 3.69%. What is the reactance on a 100 megavolt amp base? So original is 54. The new is 100 megavolt amp base. Now, what is the reactance here in the new? We will multiply 0.0369, which is 3.69%, times 100%, which is the new base, over the original base. What was the new? This is the new, and this is the original. So it's going to be 100 over 54 gives us 0.0683 per unit. So in the new base, our leakage reactance would be 0.0683. Now, transformer reactance is often specified as percentage, as I mentioned. For example, 10%. This is the per unit value divided by 100 on the power base of the transformer. Now, another example, we have a 350 megavolt amp, 230 to 220 kilovolts transformer. So the primary voltage is 230, the secondary is 20. And it has a leakage reactance of 10%, which is pretty high actually. What is the per unit value of on a 100 megavolt amp base? What is the value in ohms in the 200 kilovolt side? Now, again, using the previous example and the equation, the leakage reactance would be 0.1, which is the 10%, times 100, which is the new, over 350, which is the original. And by the way, this is 10% new and original. Which gives us 0.286. Just give me a second. Now, to find the value in ohms, what we do you remember? We multiply that per unit times V squared, which is 230 kilovolts, over the new VA base, which gives us 15.1 ohms. So again, it's going to be the XE per unit times V square over S base. Now, quiz number 2 question. We want to change the per unit impedance from one base to another. A transformer reactance is 0.1 per unit on a 50 megavolt amp base and 13.8 kilovolts base. So the base power is 50 megavolt amp and the base voltage is 13.8 kilovolts. We want to find the new per unit reactance on 100 megavolt amp base and 13.8 kilovolts base. Mhm. Yes, in this question, only the power base changes and the voltage base does not change. It's the same. Yeah, it's the transformer reactance is per unit, per unit, and we want to convert it from 50 megavolt amp base to 100 megavolt amp base. Okay, have you solved it? Now, the per unit for the new base is going to be the per unit of the old base times S of new over S old, or original, in other words. So the new reactance would be equal to 0.1 times 100 over 50. That's it. This would be equal to 0.2 per unit. So the new is going to be per 0.2. As simple as that. Now the second question, we have changed both the base and the voltage. So both the base and the voltage have changed, and our per unit is 0.18. And now we want to find the new per unit reactance on the new base of power and the new voltage base. I will give you again several minutes. Think on this and then I'll solve it. Did any of you solve it? Do you need more time? Pretty close, yes. Yes, almost. I'm sorry? It's 0.23 something. I don't know, maybe my calculations are wrong. You can double check it when I'm... So the new per unit reactance would be equal to the old per unit reactance times, and I can use this equation over here to solve it. Yes. So I can use this, and it's going to be S new over S old multiplied by V old over V new in a power of 2. So the new per unit reactance would be equal to 0.18 times the new, which is 100. The old was 50 over 50, and the old was 11 over new, how much was it? 13.8 in a power of 2. Now this would be 0.18 times 2 times 0.7971 in the power of 2. This is based on my calculation. You can double check it. Now xp new would be equal to 0.36 times 0.6354, which gives us 0.2287. Or if we want to round it up, 0.229 or 0.23 and per unit. Okay. I think that's, I would solve more, I would provide you with more problems in your homework as well. Now, to connect three-phase transformers, we have 4 different ways to connect three-phase transformers. We can do Y delta, we can do Y, Y, we can do delta Y, and we can do delta, delta. Okay. Now, this picture shows Y-Y connection. Usually three-phase transformers are constructed so all windings share a common core. So these cores are actually the same core. And it has like 3 different spacing. I would show you a picture of it. But the thing is, when they have a same core, they have interactions between the magnetic fields. And again, we have YY, by the way, the 4, we have delta delta, we have delta Y, and we have Y delta. And you can see the connections. By the way, the dots shows the direction of the current. So this dot means the current is going inside here. This dot means the current is coming out from this end. It's not coming out from the other end. And so on. So current going in, current going in. And you can see in a Y connection, all these are connected to a single point, which is the middle point. And on the other side as well, they are connected. But when you have a delta connection, they are not. They are just connected to each other. So this one is connected to this one, and this one, and this one, and this one. So by just looking at it, you can determine if one of them has the other side of the wires all connected to a single point, it's a Y connection. If they are connected in series, it's a delta connection. Now this one is a delta. On the left, it's delta, you can see. And on the right, it's Y connection. And this one is Y delta. Now, in the next class, I would explain the benefits of each transformer. We will solve the per unit model for it and how we do the connections and how we do the modeling for that. And just a quick recap of what we learned. We already learned that transformers are non-ideal. This model that you can see here is for an ideal transformer, but in a non-ideal transformer, it actually looks like this. And in a non-ideal transformer, we have leakage, we have the reactance of the core, and we have also the resistance of the copper or winding. And therefore, we have to put each one of these into account. We already solved the model for a single phase transformer, a non-ideal. The next class, we would do it for 3-phase, and we would do per unit for 3-phase as well. Thank you so much. Again, that's a lot of material to cover. We will continue next week. Thank you. And I will post the homeworks this week, and I'll give you 10 days to solve them. Thank you.